Hello students, welcome to Heat 03, Thermal Conduction in Metal. This is part of the lab offered by the Department of Physics and Material Science as Fundamental Lab from Chiang Mai University. So what is thermal conduction? So when you talk about thermal conduction is when you have two pieces of materials or two object that has different temperature. When you put together, the energy would flow from the higher temperature to the lower temperature. So if you let the heat flow until it reach the equilibrium state, so this is gonna give you what you call the heat gradient. So whenever you hear the term gradient, is the difference in any properties over the distance. So right here, if you have the hotter object at distance 0 and the colder object at T2 on the distance L, then when you put these two objects together, then you can actually measure the temperature that continuously drop as the distance increases. So if you control the temperature on one side to be T1 and the other side to be T2, then if you measure the distance, the temperature at a given distance is gonna drop linearly. So this is what Fourier is described as the temperature gradient, and this temperature gradient is going to determine how fast the thermal energy Q is going to be transferred between the 2 points. And it's not just that, but it also depends on the cross-sectional area. So as you would imagine, the larger area would give you larger pathway for the thermal energy to transfer, and then K is the thermal conductivity. And this is the key point of this lab that you'll be working on. So first, in order to determine the heat transfer, you need to find what is the temperature gradient of the setup. So in this setup, you're going to have the hot side and the cold side given as this Searle experiment. So this Searle experiment is you're going to intentionally heat one side at a constant temperature by putting boiling water, and then the vapor would come in and then heat this side. So this side is going to be the hot side, and then as the vapor comes in, it's going to heat the copper rod that's in the center. So the copper rod is going to act as our thermal conductor. So then as it heats up, it's going to cool down. So the water vapor would come out here. So the heat transfer is going to be given by this side and then flow out. And then on the other side, as the cold water comes in here on this side, and then it comes out a little bit hotter here. So this is going to act like a cooling agent. So on this side, we put hot vapor inside. On the other side, you cool it down with the cold water, and the cold water is going to flow in, and then you're going to measure the initial temperature T4, and then as it cools down, it's going to get slightly warmer, and you can measure the temperature T3. So these difference in the temperature is going to tell you how much cooling power does the cold water have. So again, to measure the heat gradient here, you're going to be using the information of T1 and T2 to find what is the heat gradient to determine what is the heat flow here. As we know from Fourier's equation that negative Ka heat gradient is going to tell you how much heat is being flown here. So if you measure temperature T1 and temperature T2 with two thermometers spaced out by the distance L, so if you know both temperature and then you divide the whole thing by the total distance, then approximately you can find the temperature gradient by just subtracting to the two temperatures and divided by L. And then once you know here, you can't tell what is H since you do not know K, even if you know the cross-section area. So the object of this lab is finding this K. So you're gonna be using another equation. So right here, since you know that the cold water coming out is gonna come in at a cooler temperature, and then it's gonna come out at a hotter temperature. So as the water flowing in and out heats up, that means that the system is being drained out of the energy by mc delta t at a given time. So if you keep flowing the mass inside here, if c delta t is a constant, then the mass flow, dm by dt, is going to determine what is the heat loss. So this is the heat that you put into the system, and this is basically the heat being lost. So whatever heat that is being transferred by this equation is going to be equal to the heat loss by the cooling effect. So if you equate these two equations and measure all the T's, the temperature on the thermostat, you can actually find what is the K. So the goal for this lab, as I said, find K. All right. So the experimental procedure. So in the actual lab, you're gonna have the hot temperature here, and then the cooling side here, and then you're going to be able to read the temperature by using different thermometers that are attached to different part of the setup. So in going through this lab, you're going to have like a constant flow of the water inside here, and then you're going to be measuring how much water is being dissipated. So as you measure the amount of water that amasses onto the container, so first you need to measure the weight of the container, and then you add more water, and you measure the time that the water flows. So then that's going to give you the dm by dt, because you know that the mass changes as time goes on. And then you keep measuring more of the water, and as you have the mass change over time, then you can calculate dm by dt. And then since you know that C is the specific heat capacity of the water, multiply that by the temperature difference between these two number here, you can actually tell how much energy is being lost. All right, and in the meanwhile, you can actually determine the heat gradient by measuring T1 and T2, given the equation that I mentioned earlier. So to find the constant K, so since K is a constant of the material, is an intrinsic property. So for example, this case is the copper rod, so you're going to find the thermal conductivity of the copper rod. So if you equate the equation of the heat transfer and the cooling power of the of the of the cold water that goes in. So if you equate these two heat, you can actually find K by dividing everything with these multipliers onto this side. So then if you measure the mass that changes over time here, you can calculate dm by dt from the slope. And then if you wait until the temperature reaches the thermal stability, thermal equilibrium, so then you can actually get a constant T3, T4, T1, T2, measure all this stuff, put it here. And then the length of a copper rod is going to be given in the instruction, and this is the heat capacitance, specific heat capacitance of the water, and A is going to be the cross-sectional area of the rod. And then once you know all of these constants and measure all of these numbers, you can actually determine K of the setup from the Searle experiment. All right, okay, so please enjoy the lab. Thank you.